Guys, so today we're going to be looking at acids and bases, and the first thing that we're going to look at is the properties of acids. So we know that acids, they generally have similar properties, and they are corrosive. Okay, they are very corrosive. That means they can eat away at materials like stones, metal, and flesh. We know that acids, they have a sour taste. If we taste lemon, vinegar, we notice that they have a similar taste, which is sour. They also contain, which is very, very important to us, guys. This is very important to us. They also contain hydrogen ions. Okay, it is these hydrogen ions that are responsible for those properties of acids and bases. Well, those properties of acids in this case. So here we have some examples of some acids that we find in the lab. All right, ethanoic, hydrochloric, nitric acid, sulfuric acid. What do these all have in common? They all end in acids. Very good. If we look at this diagram here, we have vinegar. All right, and then what about this right here? Remember, in the stomach we have a very, very strong acid, and we know that the name of that acid is, who knows the name of that acid? Very good. Hydrochloric acid. Okay. So now we have some properties of bases. Okay. First one is they feel soapy. Okay. If you touch bleach, if you touch soap, the first thing is it feels very, very slippery, soapy. Okay. The next thing is we know that alkalis are soluble bases, but like acids, the bases, they can burn the skin. They can also burn the skin. They are also corrosive. Another thing is, which is very, very important to us, is that they contain the hydroxide ions. So bases contain hydroxide ions. Okay, very, very important to us. And then the next thing is they taste bitter. If you put a base inside of your mouth, it will have a bitter taste, but I do not advise you to do that. So here we have some examples of some alkalis that you would find in the lab. You have ammonium hydroxide, calcium hydroxide, sodium hydroxide. Okay, so these are some examples of some alkali. All right, but in your everyday lives, bases, alkalis, these are used as cleaning. Okay, they are used for cleaning. Okay, they're used in cleaning. Cleaning products, you have soap. All right, these are all alkaline. So right here we have some examples of some cleaning products, and we say that all of these cleaning products are bases. Okay, so one of the uses of bases is for cleaning. I see bleach here. Okay, and I see some other cleaning products. Okay, these are all bases. Most of bases are used for cleaning.
This is Dr. B. When we talk about strong acids, we're talking about acids that dissociate completely in water. You can think about dissociate as breaking apart, forming ions, or even dissolving. So let's talk about HCl, hydrochloric acid, a very common strong acid. We put HCl in water, and it's going to dissociate completely. That means we have our liquid HCl, our strong acid, and our water. We put them together, and the H's and Cl's dissociate. They break apart into H plus and Cl minus, and they're dissolved in the water. Some common strong acids, and commit these to memory, they're important, are hydrochloric acid, sulfuric acid, and nitric acid. Other strong acids you might see: hydrobromic, hydroiodic, and perchloric acid. For weak acids, only some of the hydrogen atoms dissociate to form the H plus ions. Most of them will stay bonded to the acid molecule. Here you can see for this weak acid molecule, acetic acid, the hydrogen ion is only dissociated part of the time. In a larger sample with more molecules, only some of the atoms would be dissociated at any given time. A good example of a weak acid is acetic acid, CH3COOH. And it's important to note that the H at the end, that's the one that comes off to form the H plus ion. You should be familiar with this equation because it comes up quite often in chemistry. Other common weak acids, we of course have acetic, hydrofluoric, and hydrocyanic acid. Let's try some practice. So looking at the image, what type of acid would this be? The answer is, since they're dissociated completely in water there, this would be a strong acid. It would also be dilute because there's not very much of it. Now try this one. You can see there are quite a bit of the Cl's and the H pluses, and that the H pluses are all dissociated. So we can tell that this is going to be a strong acid. It's also going to be considered concentrated because there's quite a bit of it. So what about HF, hydrofluoric acid? Well, since most of the H pluses are still attached to the molecule there, they're not dissociated, this is going to be a weak acid. It's going to be concentrated as well because we have quite a few molecules. Last one here. It's going to be a weak acid again because we only have a few H plus ions there dissociated, and it's going to be dilute because there are not very many of the molecules there dissolved in the water. This is Dr. B with strong and weak acids. Thanks for watching.
So you would have watched the video already, and now we're going to just look at strong and weak acids. So strong acids, these are acids which dissociates completely when you put it in water. What does this mean? Okay, these are strong acids are those in which their ions separate completely when you put them in water. So let's look at an example on the right. So here we have HCl. So HCl that's not in a solution is going to be called hydrogen chloride gas. All right. However, when we put it in water, when we put HCl in water, then it becomes hydrochloric acid. All right. But HCl just by itself, no, we don't put it in water, it's HCl gas. Okay. Okay. Now we put this in water. When we take this HCl and we put it in this hydrogen chloride, we put it in water, this is what's happening. Okay, it automatically splits up into H plus and Cl negative. You see how the H plus, you see how the HCl was just completely separated into H plus and Cl negative? That's what we mean by dissociate. Okay, that's what we mean by dissociate. So next we have weak acids. Weak acids, these only partially dissociate in water. These are the ones that produces a few hydrogen ions in water. The ions do not separate completely in water. So if we look at this, this is CH3COOH, which is ethanoic acid. When we put this in water, look at it. You have H plus. This gets separated into H plus CH3COO negative. Okay, it does not completely separate. You have one H plus here, and then you have this whole compound here. So it did not completely split up. Okay, so this is why it's called a weak. This is why it's called a weak acid. So now we have strong versus weak alkali, which is similar to the acids. So these again are strong alkalis. These are ones that dissociate completely when you put it in water. They split up completely. The ions split up completely when you put it in water. Keeping in mind that the ions are going to be, you're going to have the hydroxide ions going to be produced in any base solution. You should have an hydroxide ion being produced. So this is why you have hydroxide here, and then you have the other thing that's attached to the hydroxide is the Na, and you see that they both completely separated. So that's why it is a strong alkali. Now the weak ones, these only partially dissociate in water. Let's look at ammonia. So this is ammonia. When we put it in water, all right, we have the hydroxide ion, but then we also have this. We still have the nitrogen and the hydrogen still tightly bonded together. So this is why it is very weak base. So now we're going to look at the basic oxides. We've watched the video already. Now we're going to look at basic oxide. Okay. So the first thing is when we see these things, we see these things. What are these? Are these metals or are they non-metals? Okay, yes, these are all metals. And what's happening is we are going to be burned. These are going to be burned. When these metals, when they burn in the air, okay, when they burn in the air, they're going to form basic oxide. All right, now, so we have our first metal here is potassium. If we combine it with oxygen, all right, Oxide means we have oxygen in there. Alright, so potassium and oxygen gives us potassium oxide. Sodium in oxygen gives us sodium oxide. Lithium and oxygen gives us lithium oxide. So these right here are all examples of basic oxides. So next we have sulfur, carbon, and nitrogen. And what's going to happen is when we burn these, alright, these are considered metals or non-metals. Non-metals, yeah, so when we burn these non-metals now, what we're going to form is what kind of oxides? Acidic oxides. Okay, so non-metals, when they burn in the air, they form acidic oxides. Okay, so sulfur dioxide, sulfur, all right, plus oxygen should give us sulfur dioxide. Carbon plus oxygen gives us carbon dioxide, and nitrogen plus oxygen gives us nitrogen dioxide. Okay, so these are all examples of acidic oxide because they are non-metals, and when they burn in the air, they're going to form acidic oxides. So why do we call these acidic and basic oxides? I know you were wondering. So we said that metal oxides are called basic oxides, all right? And these are some of our examples. This is because these metal oxides, when you put them in water, what are they forming? Look at it. Calcium oxide forms calcium hydroxide. Zinc oxide forms zinc hydroxide. Barium oxide forms barium hydroxide. And when we measured the pH was greater than 7. So that is telling us that the pH is that of a base. Okay, so these metal oxides, when we put them in water, they form a base, and that's why we call them basic oxides. Now, these right here, these are non-metal oxides here, all right? We have carbon dioxide, sulfur dioxide, and nitrogen dioxide. And when we put these in water, we form carbonic acid. CO2 forms carbonic acid, SO2 forms sulfurous acid, and HNO3 forms nitric acid. We measure the pH is going to be less than 7, telling us that it is an acid. All right. Also pay attention to the SO2, sulfurous acid, and the nitric acid because these two are the problem that we face, all right, called acid rain. Okay, so we know that sulfur dioxide and nitrogen dioxide, when they combine with water, they give us this right here, H2SO3 and HNO3, which is called acid rain. Okay. So now we have amphoteric oxide, and these amphoteric oxides, they can behave both as an acid or it can behave as a base. It has both basic and acidic properties, and the examples of these are H4. Can you guess what H is going to stand for? H is for water, H2O. You also have A for aluminum oxide, and then you have zinc for zinc oxide. These are all amphoteric oxide. Now we have neutral oxide, and these neutral oxides, we have no, both for acids and base. This is because these oxides, they show neither basic nor acidic properties. So they're not going to behave as an acid, or are they going to behave as a base? And as a result, we call them neutral oxide. And we have two examples, carbon monoxide and nitrogen monoxide. So now we have a Venn diagram. We're going to complete this Venn diagram for the different oxides. Okay, so we're going to first label them basic, acidic, neutral oxides. All right, and now some basic oxide. What are some examples of some basic oxides? Remember, these were metal oxides. Okay, so we have magnesium oxide, metal, and oxygen. You have lithium oxide, metal, oxygen. You have calcium oxide, metal, oxygen. Next, we have some acidic oxides, all right? Carbon dioxide, all right? So you have non-metal, carbon, and oxygen. Then you have non-metal, nitrogen and oxygen, nitrogen dioxide. Then you have sulfur dioxide, non-metal, and oxygen, okay? Next, you have neutral oxide, and we know that neutral oxides will neither react as an acid or a base, and those are carbon monoxide and nitrogen monoxide. And then we have, of course, amphoteric oxide. It can behave both as a base or as an acid. So we can put them right in the middle here. So that would be our aluminum oxide, water, and the zinc oxide. Okay, so make a note of this, and you should use the same little chart for you to study the different oxides.